We have a practice data set, which we'll be using for the whole of the class and for your homework. So the practice data set has already been shared. That's the link there, and that's the QR code there as well. And the goal of the whole course from beginning to end is to build data literacy. Think of literacy when we say somebody is literate. It means they can read, they can write. It means they can understand context. It means they can communicate. If you give them a book to read, they can read that book and tell you, well, this book is interesting. This is the story behind the book. So they can do all of those things. It's not just reading words, but you read the word and you get the meaning, and you can pass that meaning to someone else. So that's the goal. And we want to do the exact same thing with data over the next 4 days. How do we read data? How do we write data? How do we read not just words, but context? How do we get the meaning from the data so that we can communicate to others? The goal is that if someone gives you a data set, you should be able to take it and make sense of it and say, well, here are the big findings from this data set. So that's the goal we're trying to achieve over the next 4 days. All right, since we're all going to be data scientists or data analysts, there are some basic terms, not many of them, that we need to be on the same page. So we'll talk about data sets and data frame. Anything that has data is a data set, right? But not all data sets are data frame. A data frame, think of a picture frame. A frame on the wall always has, it's like a square, and then that's exactly what should come to your mind when we hear the word frame, data frame. So a data frame is a squarish data set that has rows and columns. So think of Excel spreadsheets. When you look at Excel, that's the first thing that comes to your mind. You see all these columns and all these rows. That's what we mean by a data frame. But as an analyst, you should be aware that data comes in other forms that may not be a data frame. And we'll look at some of those today. There are different types of file. Obviously, we can't talk about data analysis without introducing you to different file types and file sizes. We need to be aware of those things. So, and then we also need to be aware of FAIR standards. FAIR is something we're going to be mentioning over and over and over. FAIR standards means data must be findable, accessible, interoperable, and reusable. So that is a very, very common terminology among people who work with data. So since we're introducing you into the field, you need to know FAIR standards. And it's important for you to know that because that guides every single thing you do. So when you are renaming a variable, for example, you want to make sure that you rename it in such a way that it is FAIR aligned, that even if you export that data set from whatever software you're using to another one, it won't cause problems, right? So FAIR is a song we sing all the time. How do you ensure that whatever you're doing meets the principles of FAIR? Findable, accessible, interoperable, and reusable. All right, now let's see what we've just discussed here. So this is not just going to be slides and presentations. I have 16 slides, but I'll be breaking them, and then we'll do some hands-on in between series of slides. So let's look at some of the types of data sets, the common formats you should expect. So here I have some data sets. So everything here is a data set, but not everything here is a data frame. Take note that all of them here are all the exact same data. I just converted them to different types of formats just to demonstrate. Your first job as a data analyst is to know file types. You'll be a really horrible data analyst if you can't recognize file types. And you don't have to memorize anything. You need to learn how to, some of them are pretty recognizable. For example, you can easily tell an Excel from a CSV. Both of them have X because they're all, they look similar. Excel has this, this icon here beside it, while the CSV typically has this A, whatever, right? But you don't have to memorize that. When you have a file, you can easily check the properties. You right-click on it, and you go to Properties, and you click there, and I'm using two screens, sorry, it appeared on the other screen. And so you see this is the properties of a file. That tells you every single thing about the file that you need to be aware of. You can see the file's name. You can see the type of file. Now, this point here is the format here, .xlsx. That tells me that this is the file type. So that's what we call the extension of a file, all right? So you need to be able to spot those things easily. So when you have a file, just develop a practice that take the file, check its properties, because not all files might come in the format you're used to. If you're working as a data analyst in a team, you will be exposed to several different types of files, some that you have never seen before. So you must be able to recognize or be able to find out the type of file you're dealing with. And so when you also open the properties, you want to look at a very important, if two things you really want to pay attention to. One is the type of file, which is the extension type of file right here. The other is the file size, right? You have to know file sizes because you should know that if the file is very massive, okay, this might take a lot of time, maybe analyzing it, or maybe depending on your size or your memory. Also, depending on whether you are doing analysis over the cloud or on your machine, those things could impact the length of time it takes to just complete an analysis. So become very familiar to inspecting a file, a data set, and being able to read it. So we said that we have data frames and data sets. So all of these things here are data sets, but not all data sets are data frames. So let me show you an example. This is let's open the file type by clicking on properties. And let me pull it over here. This is an XPT format. XPT is a SAS transport file, XPT transport, or cross-platform. XPT format was designed to be a format where you could transport it from one platform or one software to another. So it's not designed to be a form where you can read it. It's not human readable. So if I open this file, for example, it would look like completely gibberish to you. Let's open it quickly. All right, so see, this is a SAS transport file. It doesn't make any sense, right? Well, when you as a human being look at it, it doesn't make sense because it's not designed to be read by humans. So it's machine readable. So in this case, this is a file that is a data set, but not a frame, right? It's not like when you open Excel and you see nice little rows and columns, right? So this is an example of a file. So again, you need to know the file you're dealing with. And then the other file types, again, another very important thing for us to do when you open a data set is to just open it and read it. Never ever develop the habit of you grab a data set and you just go and import it without, at least if it's in Excel or CSV, develop the habit of just opening it first. So here I can see that, okay, this makes no sense. I expect this to be in nice little columns and rows, all right? So yeah, this is one of the things I want to make sure that we can assess. So, but the bottom line here is that when you get hold of the file, try to see what it is. Is it a SAS file? Is it a SAS transport file? And you need to know the different types of formats because sometimes we have a problem and that can only be solved with a particular format. Take, for example, this format here. Let's see the properties. Okay, it opens here. So here, this is a .parquet, right? A parquet format is a very useful format in data science, data analysis, because it is a very portable format. So all of these files are exactly the same file. But if you check here, this file, if you look at the size here, the size of this file is 524 kilobytes. Again, as we're all data scientists and data analysts, you must know everything about file sizes. Your kilobytes and megabytes must be your second name. You must know these things very well. So there are 1,000 kilobytes in a megabyte. So take note that this is 528 kilobytes. This is the exact same data set. Now, I'm going to keep this open and let's compare this to this data file, for example. Let's check the properties. And let me pull it over. So this exact same file, this data file is 1.89 megabytes. Remember, that the other one was 0.5, 0.3 kilobytes, 0.3 megabytes rather. So a package file is like 10 times smaller than its corresponding format in Excel or Stata. So it's a very, very valuable format when you have a very massive data set and you don't have a lot of storage, right? So your job is to also know the formats and know that, okay, if I have a very massive file, I have to maybe convert it into a parquet format, just so it's easily stored and doesn't take all the space on my computer. It's a very compressed format. So that's why you need to know the different formats. And these are the key ones I have just presented here, so you can know them. So that's why a parquet format is very important to us. And so let's now see how we can read that and convert, because obviously if it's important for you to create this, you should be able to read it and create it. All of the analysis we're going to be doing today will be on the chi-squares platform. And so we'll show you how to do all of those procedures. If you are using other software, the type of file matters, because there are special instructions to read, for example, a parquet format versus a CSV format versus a Stata file. Those differences then matter. For example, if you're using Stata for your analysis, you'll have to know a different command to import a package format or whatever the other format. On the chi-squares platform, however, that's streamlined. You don't need to know a specific command. It's the same. All different file formats just have the same format for importing them into the platform. So let's go ahead and let's use our test data set. This is our test data set if you have access to the link. So we're going to be using it for all of our operations for the next 4 days, including today. So let's say that you are working on a CSV file and you have to generate a parquet format. How do you do that? Well, I would log into my account and go straight to data analysis. And let me create a new project. And let's call this day 1 of data analysis. All right, let's proceed. And I'm going to upload my data sets. All right, data set has been imported already. So the chi-squares platform reads data from any single format. If it's data set, we're going to read it. If it's data frame, we're going to read it. It doesn't really matter. And all you need to do is just import it that same way every single time. You can import data from recent files, from your storage. You can upload from anywhere it is, whether it's in a Dropbox, in a Google Drive. If you have a survey that is currently ongoing on the platform is a one-stop shop for everything research. So you can conduct surveys, you can do anything. So if you have surveys, you can also import from them. And we also have a large and growing number of public data sets that we are cleaning and standardizing and making accessible to researchers. You can also import directly from public data sets. But there's nothing special to do to import a parquet file versus a CSV versus an Excel. It's the exact same thing. So if you want to export data, you come to Actions and you click on Export. And these are the file formats that we make available for you to export into. Of course, first on the list is parquet, because that's an extremely important format for data scientists. We use parquet format a lot. So if you're interested in this career path, well, you better get used to working with parquet formats. You can also import to Excel, to CSV, and as a JSON file. Well, as data analysts, you would not necessarily need to use a JSON file so much. We use it a lot in engineering, where the front end and the back end must be able to read the same file. And so that's why that format is important. But if you're just trying to analyze data, that may not be your preferred format. So it's important for data scientists, but not data analysts per se. Well, since this session is for data analysts primarily, I will not go too much into that. So, but this is how you can export files. You come to Actions, Export Data, and you choose the format you wish to export to. So if I wish to export as a parquet file, I'll simply click on this. And this is my file there. So I can then grab it. And so that is how you can import data and you can export data from the Chi-Square platform. All right, going back to my slides. So the terms, again, every data frame is a data set, but not every data set is a data frame. A data frame is like rows and columns. A JSON file is not a data frame. Let's show you what a JSON is for those of us who are curious. Let me go back to my files. Because even if you're not going to be using it, you should know what it looks like. So let's see. Okay, it's opening on this. Sorry, I'm working with two screens, so it's opening on the other one. Let me pull it to the side. So this is what a JSON looks like. Again, it may not make a lot of sense to you. So like you see, it's not as structured as a rows and columns. It's still a data set, but it's not a frame, like where you have nice rows and columns in Excel. But they are interchangeable, right? So all of those files which we saw earlier, and this is how you know it's a JSON. It's going to start with this brackets, right? And then these are your variable names. So this is an example of a data set. All of them are data sets like we mentioned, but not all data sets are frames. So let's go and see which one is a frame. Let's open this one so that we can, again, this is what we're used to seeing. We have rows, nice rows, and we have nice columns, right? This is like a picture, a frame on the wall, and this is what we call a data frame. And so if you're going to be working of course, in an environment to analyze data, most platforms are designed to work with data frames. So, but again, from a perspective of nomenclature, that's what we want to emphasize on that slide. All right, now let's go on to our goal for analysis. For those of us who are healthcare providers, you know that when a patient comes to your hospital or to your clinic, you don't just go and grab the patient and start to, examine them. In med school, they teach you about IPPA, inspect, percuss, palpate, auscultate, or whichever the order is. That's the exact same thing we do. So a patient comes, what do you do first? You take a history from them. And then after you take a history, if they have a tumor, you don't just go and start touching it. You inspect it. You look at the edges symmetrical. Is it swelling more on one side or the other? Are there color changes on the surface? Is it textured? Those are things you can see by just inspecting. At this point, you're not touching the patient yet, right? And then palpate. Now you can touch with your hands, right? Palpation is always just with your hands. You don't palpate with an instrument. You use your hands to just touch and say, okay, I can feel this beat, or I can feel this. And then you auscultate, right? Now you're bringing an instrument. That's the exact same thing we want to do with analysis. Every single time you have a data set, you want to do these 4 things. Take a history, inspect, palpate, and auscultate, right? Do not miss that sequence. So let's see what each of those things mean. History. If somebody gives you a data set, remember we said the goal is to train you to work as a team. So you are a data analyst in just a team of other people. Maybe you have an epidemiologist on that team, you have a sociologist, you have your boss. Somebody gives you a data set. Don't just take the data set and say, okay, I'll give you an answer in 1 day or 2 days. It's like, okay, are you a magician? Now, here is the kicker, right? People who are new to data analysis or data science, they imagine that, oh, if I ask questions, it will mean I don't know what I'm doing. No, if you don't ask questions, it is clear that you don't know what you're doing. So somebody asks you a question, take a history first. So you can use the interrogative pronouns. What, where, who, how many, why. So like ask the person who gave you this data set. So this data set, where is it from? How did we get it? Who is in it? How big is it? Of course, you're going to look at it later. You're going to get your answers, but it gives you a framework, a benchmark. If the guy says, well, ballpark, I think there are about 20,000 people in the data set, and you import and you see just 200, clearly there's a problem. So the goal is to have context. You don't get context by reading the data set or by looking at the data set. You get context by asking questions and getting a clear history of where the data set came from and what it's all about. So make sure you ask all those questions. What, where, who, how many, and why. How were data collected? And please, if somebody gives you the data set, you must ask for documentation. Is there documentation for this data set? Is there a data dictionary? You look very ridiculous if somebody gives you a data set and there is no documentation and you just go. I would be very concerned if I gave an intern a data set and they did not ask me for documentation for the data set. Because I'm like, okay, are you a magician? How are you supposed to know what's in the data set? So please don't make that mistake, right? Because then it kind of pokes holes at your credibility as a data analyst. Because the data must have its data dictionary. That context must be there. And if there is no data dictionary, well, you need to ask questions. Again, all those questions we mentioned, right? Don't have a scenario, read my mind, where you're supposed to. I also ask the person, so what are we trying to do? What's the big picture with this? What are we trying to achieve? Or what do you have in mind? So if I give a data set to an intern, I expect them to ask me questions. Ask me, okay, sir, what are you thinking? Like what are we looking at? What's the issue of interest in this data set? Don't just take a data set and just go off your way and start just analyzing, right? That misses the whole point of analysis, which is to add value, to answer a question that is of interest to the team, not of interest to you. So please, the moral of the story is that you must ask questions. You must get a documentation for the data set, a data dictionary. And if they don't know, if your boss doesn't know, you have to say, well, do you know who I can follow up with? It's not okay to say, okay, well, I don't have a documentation. Then you say, okay, all right, I'll go and analyze data. That's ridiculous, right? Say, okay, where did you get this data set from? Can I follow up with the person? And then you send an email to that person and say, hey, my name is so-and-so. I got this data set from so-and-so and I don't have a documentation. Please, can you share it? Or can you create it and share with me? That's what you're expected to do. So please, a good data analyst shows that they're a good data analyst before they even open the data based on how they collect history about the data. I cannot emphasize this enough, and that's why we're spending quite a lot of time here. Next, we'll go to inspect. All right, so now you've gotten your data dictionary. How do you inspect data? So again, remember, inspect is just, you are just looking, you're not touching. So look at the data set, check its properties. What type of file is it? Is it a Parquet file, a CSV, an Excel, a data, SPSS, SAS transport, whatever format? All right. What size is it? Then if you can open it, let's say it's an Excel file, CSV. Is there any data set in it? Like, you'd be surprised that you might just open it and it's completely empty. So open it and check. Is it empty? Do the data look properly formatted? If it's Excel, are there multiple tabs in the sheets? Are there colors? If there are colors, that's, that might flag that you might have some formats that are invisible that might cause problems for you. Are the columns of one type? Are the variable names proper? What are the variable types? All right, let's go to Excel and let's see let's operationalize what we're talking about. So let's say this is our data set, and I come here, I see a whole bunch of stuff in this. I see multiple tabs. Right. Obviously, I can't just take this data set now and then I see variable names here as, let's say sentences. Right. So here I have a problem. Let's flag this so it's very clear to us. So inspection means I can open this data set, this file, CSV, this Excel file now. So I see a lot of things that are already problematic for me. Just by looking, I can see that, okay, why do you have color? If you have color, the problem is that there might be other formats, other things in the data set that are invisible to your eyes, but are there. So for example, at the bottom there, you might have a whole bunch of, maybe some data or some images or whatever that is just there that will create a problem for you. So you want to make sure that none of those things exist. So if this is in Excel, you can just select the whole data set and come here and say clear format. All right. So clear formats removes the things, the formats that you can see and those that you cannot see that are problematic. Right. So now you want to make sure that all of those extra things are removed. If you have data that you have multiple tabs, don't try to import the whole sheet the way it is now. Because remember, you can only read data from one single tab at a time. So again, to have clear separation of concerns, make sure that your data set that you're trying to import is just one single sheet. So you can either save file and click on save as. So let's come to here, file, save as. I'm going to do this. And then I might say save as CSV. CSV is comma separated variable. If you're working with Excel, CSV is always a very good and stable format to save your data sets as, So select CSV and give it the name and click save. Right? It's going to tell you that the selected file type does not support workbooks that contain multiple sheets. That's fine. So it's telling you that this is a no-go. We can't do this. So you just say, yes, I want this active one, right? So that's how you take care of that. So inspection is very important. Before you even import your data, if it's in Excel or CSV, open it up and just see, does it make sense? Do you have variable names that do not make sense? Of course, it's not practical for you to go through every single variable and say, okay, are the names correct? But just take a quick look. That's what I'm saying, right? Take a quick look. And so those are some of the few things. And then just scroll through the data set and see, are there things that jump out to you? Are there, and sometimes it might be very discernible that, okay, there's some whole chunk of missing thing here. But just look around before you jump into importing the data and analyzing it. That's just good practice. So that's what we do with inspection. The Chi-Scores platform has inbuilt capabilities to inspect your data for you when you import it, so that if there are problems, it's going to flag it for you and say, well, your variable names are not correct, right? But you should develop the habit of just inspecting your data sets before you import them. So are the variable names proper? What are the variable types? Is it categorical, discrete, continuous, date, string? We're going to show this in a minute. We're going to import our data set and look at all of those things step by step. And then you look at the variables fit for use. For example, do you have indeterminate variables? For something to be a variable, it must vary, right? If that's why we call it variable. That means that its levels vary. If you have a variable that is only one value, one unique value, then it's not a variable because it doesn't vary. So if everybody in your column has a value of 1, or everybody has a value of 0, that means it doesn't vary. So you can't really use it that much. And so this is what things we want to do with inspection, right? Import data in and make sure that everything is fine. And inspection is also very important because sometimes, again, you open the data set and you realize that, oops, this is actually not created well. So this is the bad data I was showing you earlier. You might just say that, okay, this doesn't look right. Maybe the person who exported the file and sent it to you didn't do it properly. And so you end up with something like this, such that when you try to import it, you're going to have problems, right? So inspecting allows you to make sure that everything is fine. So you see, at this point, we've not even touched data yet in terms of trying to generate estimates or analysis. But this is just preliminary steps that we have to take to make sure that everything is kosher. All right, so let me import. We've imported our data set. So how do we inspect? Well, first things first, let's look at the very top here, right? We look at the number of columns. Is it what we expect to see? This is what we call the dimensions of a data set. A data frame has 2 dimensions, rows and columns. So you want to check the number of columns that you have and the number of rows you have. Again, that's why you in the history you ask the boss, hey, like, so how big is this data set? They give you a random number. Oh, I think it's about 20,000 people, or I think it's about 10,000 people. So you already know what to expect. So you can then check against this to make sure that it makes sense. If you don't know what to expect, you have to check against the documentation to make sure that what you're seeing is what you're supposed to be seeing. If the documentation says that there are, for example, 3,000 people in the data set, well, if you import your own data set and you're seeing 1,000 people or 500 people, well, that's a problem. So please, don't just import the analysis and then say, okay, now let me go and run my regression. No, right? You got to calm down. Look around, make sure that you have the appropriate number of columns, the appropriate number of rows, and then go through each of the variables that are important to you and make sure that they are appropriate and they're well captured. On the chi-source platform, there's a visualization to make it very clear to you what type of variable it is. So these 3 lines represents categorical variables. This represents string. So remember the type of variables we mentioned, you could have categorical variables. Categorical variables are things like gender, male or female. They are ones where you have each of those categories are sort of repeated. So in a data set, you might have, for example, male, 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 female, female, then male, male, male. So you can see there's some repetition in the categories. That's the difference between a string variable on one hand and a categorical variable on the other hand. So a categorical variable, you can look at this variable, for example, email. Well, the emails don't repeat each other. They're like each email is almost unique. So if we have 10,105 individuals in our data set, if there are no missing values, well, you're going to have 10,000, that exact same number of emails. So there's no repetition in the categories or the unique values. And that's what makes a string variable, that you have a very high degree of uniqueness of each of the unique values. Unlike, see here we have first name. This is classified as categorical because there are just 5 unique values. Unlike here, there are 10,145 unique values, right? And so that's what makes a string variable a string variable. And so this is how it's represented here visually, so you can see what it looks like. Then this is continuous variable. Continuous variables are variables that have things like floats. Again, we should add that to our term. Let me add that to our data analysis terms that you all have to be very familiar with. Let's add a new term, floats. So floats are, think of them like decimal places, right? So again, you need to know these terms because when you're speaking to other data analysts or data scientists, they're going to be using those terms in their conversation a lot. So you need to understand exactly what they are saying. So if they say a variable is a float, what they mean is that the variable has decimal places. So so variables that have decimal places are floats. And so the reason why we need to know the type of variable is because the kind of analysis we do is determined by the type of variable we're dealing with. So here you can see the float variable have a visualization of a scatter plot, so you can know that this is continuous variable. And then we have binary. On the chi-source platform, binary variables are treated as a separate class of variable. And that's important because there are certain statistical procedures that require the variable to be in binary format. And so that's why you have 0, 1, 1, 0. So that's what binary means. In this case, on the platform, a variable like, let's say, gender, even if it exists as male and female, let's see, sex. So see, this one has 2 unique values too, but those unique values are not 0 and 1. So it is still classified as categorical. So that makes a very important distinction between how binary variables versus categorical variables are treated on the chi-source platform. You must be 0 and 1 for you to be a binary variable. And then let's look at another type. Then here you have discrete. A discrete variable is a variable that takes on very fixed or unique values, fixed values. So you can see here that you have 1, 2, 3, right? That's just to indicate to you that the nature of a discrete variable, it takes on very well-defined values. All count variables are discrete, but not all discrete variables are count. So again, since we're all professionals in this field of data analysis and data science, again, we need to understand. Let me actually add those terms to our list of growing terminology. So we'll talk about discrete, and we'll talk about counts. And remember, we said that all counts are discrete, but not all discrete are counts. So what do we mean by that? So remember that a discrete value or a discrete variable takes on very fixed values. Think of number of children in your household, 1, 2, 3. Those are fixed values. We cannot imagine, we cannot generate a new value hypothetically, right? The values are fixed in place. So all counts are discrete, but not all discrete are counts, because think of shoe size. When we measure shoe size, they come in fixed numbers. So you can have shoe size 10, but you can also have shoe size 10.5, right? Now, in this case, counts cannot be fractions. You cannot have negative counts, and you cannot have counts that are fractions. So you cannot say a count of 10.5. That doesn't exist. It's not a thing. Counts are always whole numbers that are positive numbers. But a discrete value can take on a fraction, like we just mentioned with shoe sizes. You can have shoe size, 10.5, and it's discrete because it's a fixed value. You can't say, so you can't just wake up and say, oh, my shoe size is 10.75. That does not exist. It's not a fixed value in that context. So in that case, it's not a discrete value. So that's why we have to know those terms, because the type of analysis we do, again, is a function of the type of variable. So on the platform, you have discrete values. This is the iconology, the icon here, and you have the designation here as discrete. And so all variables, so that way you can just look at the icon immediately and know, oh, like without even looking at this, I can tell, oh, these are continuous, categorical, binary, and so on and so forth, right? This is what we mean by inspecting your data. Just inspecting to make sure that what you see makes sense. Inspecting also means that you're going to be looking at like these columns here, number of unique values, and very importantly, number of missing values. Like, how many missing values do I have? 0, 0, 0, this is good. Then I see quite a number of missing values. Now, when you have large number of missing values, in some instances, that is fine. It's not a problem. But in some instances, it could be a problem. Let's look at the first scenario where missing values are not a big deal. Missing values are not a big deal if you have a systematic skip pattern. So let's say in my survey, I have a question that said, are you a smoker? And then people who are non-smokers are skipped from answering the questions that have to do with smoking. Obviously, they will have missing values for those questions, but that's not a problem. That's a legitimate, source of missingness that has no impact on analysis, right? Because those individuals are not part of a denominator for individuals who are smokers, so they're not going to be analyzed anyway. This takes us back to the issue of context. You cannot know that context without having had the opportunity to look at the questionnaire and look at the data dictionary. So if you had obtained a data dictionary, you will see that for this variable, it will say, oh, these individuals were skipped, right? And so that way, that adds context. You can now say, oh, I see why there are so many missing values. Because this 20,000 missing values doesn't mean it's a problem. It just means that these were all the people who were non-smokers. Again, that is why context is so important. So the moral of the story is, please don't just take a data set and go and start analyzing. You must have the context. Try and ask questions. Take a detailed history of the questionnaire. You must absolutely have a code book to explain what the variables mean, and if there were key patterns. And that's the only way you can make sense of the data. You can't just know it from your brain. It's not possible, right? You have to be able to read it from a single source of truth, which is the code book or the data dictionary. And when you're working as a team, it's always a good practice to provide documentation, right? Even if you're working alone, as a good data scientist, you must develop the habit of providing good documentation, whether you are writing code or whether you're using a no-code platform like a chi-squares platform. So for example, if I want to make a note about this variable, that's why you have this notes and tags. Add notes. I'd say, this variable was recorded in XYZ because of XYZ, right? Provide documentation copiously, because same you who did this work will come back 2 years and be very confused that, oh, I wonder what happened here, right? So the hallmark of a great data analyst or a great data scientist is in the nature of a documentation they provide. So that when you invite somebody to your project, they can, if they're confused, they can just open your notes and read and say, oh, I see what happened there. So it's not just about, oh, I take a data set, I just analyze, I give result. No, we have etiquette in this profession. We have just things that you have to do right to be a great analyst. And work as a great person in the team. You're not working alone. So always remember that. So look at number of missing values. And if the missing values is just a lot, 10% or more of missing values is a huge problem for you, right? And the reason why it's a problem is because of the issue of bias. In research, bias means there is systematic error, right? And we generally talk about 3 types of biases in epidemiologic research or research in general. We talk about confounding bias, measurement bias, and selection bias. Now, the reason why missing values are a problem is because of selection bias. Now, in this case, we have, let me look for a variable that has a lot of missing values. We have 4,406 individuals who have missing values for medical condition. Now, the question is, the people who have missing values and the people who don't have missing values, are they the same people? If they're the same people, well, fine and good. The missing values, sure, it's still a problem from a perspective of precision, but not a problem from a perspective of validity. Let me add those 2 terms to our sheet again that are important for us to be aware of. Validity and precision. If you are doing data analysis, you're not just worried about statistics. You also have to worry about the epidemiologic basis for everything you're doing. I cannot emphasize that enough. So it's not just about statistics. Statistics is just a tool. Epidemiology gives it life for you to interpret the results, right? So let's not worry about a tool. I think the common problem with a lot of people who want to do data analysis is they always engage in this very meaningless debate. Oh, which software is better? Like really, like it doesn't matter. Like, what are you doing and how do you interpret the results, right? So it's not just about the stats, it's also about the epidemiological basis of what you're doing. Now, when it comes to, so let's break down those 2 terms so that we're on the same page. Validity means it is correct, it is accurate, it is true. That's what validity means. Precision means that your confidence intervals are narrow, right? So a precise estimate is one where the confidence intervals are very narrow, right? So if you have an imprecise estimate, your confidence intervals will be very wide. So again, let's take a step back. Research or statistics is all about saying, here is my answer, and here is how sure I am of it, right? Those are the 2 things we're always trying to capture when we do data analysis. What is the answer, and how sure am I of this answer, right? If I say, oh, somebody says, oh, there's a guy giving some money on the streets down the road, I'm going to say, how sure are you? Like, if you say, oh, well, I am 60% sure. You see, there are 2 things involved there. You've given me an answer, and you've given me how sure you are of the answer. So please freeze that concept in your brain, right? Everything we do in analysis is always captured around those 2 things. What is the answer, and how sure are we of that answer? So that's why we calculate point estimates and we then go ahead to calculate confidence intervals. The point estimate tells us the answer. The confidence interval tells us, well, how sure are we, right? So the point estimate, when we talk about validity, we're talking about the answer itself. When we're talking about precision, we're talking about how sure are you? Those two things always go hand in hand. An answer and how sure are you? An answer and how sure are you? Again, the estimates and the variance. So the how sure are you is called the variance, and the answer is called the point estimate. The variance can be measured with many, many things. We'll measure it with standard error, we'll measure it with sampling error, we'll measure it with confidence intervals. Again, we're not going into the technical details, but again, big picture, we need to understand those things, because analysis is not just about creating an answer. The answer has to be rooted in science and in truth. So that's why we need to add those two terms to our lexicon. Validity has to do with the answer. Is this answer true? Precision has to do with how sure are you? Are you very, very sure? In which case your confidence intervals will be very narrow. Or are you very, very unsure? In which case your confidence intervals will be very broad. Now you're going to be asking, what does this have to do with missing values? Well, missing values affect both of these things. Missing values can have an impact on validity and on precision. How? Well, if your missing values are in a way whereby the people who left, who are missing, are kind of different from those who are in your data set, now you have a problem of selection bias on your hands. So let's go back to our data set. So let's say that in this variable here, people who have a medical condition are more likely to be missing in a data set, right? So most of these 4,406 people, it's not as if half of them are missing. Half of them are people with a medical condition, and the other half are people with a medical condition. Is that maybe most of them are people with a medical condition. Maybe people who have a medical condition were rushed to the hospital in the middle of a survey, or maybe they don't want to answer the question because they feel, it's sensitive and it's invasive, well, for whatever reason. Then we have a problem of validity, because there's selection bias there. But it's not just validity that this affects, right? Remember that when you have a lot of missing values, it means that the number of people that we have data for becomes smaller. So forget about the sample size of, forget about this, this 10,175 people here. The number of people you have for this particular variable is much, much smaller, all right? That means that your estimates begin to have wider confidence intervals, meaning that they are not so precise anymore. That's why you need to care about missing values. That's why you have to inspect, right? So as you're inspecting, it's not just about, oh, I see there are 3,624 missing values. No, that's not what we're asking you to do. What we're asking you to do is that as you're inspecting, you have to be thinking too. So you're inspecting and you are thinking at the same time and saying, okay, wow, I have a lot of missing values here. I know that this is going to affect validity if the people missing are different from the people who are not missing systematically. And I know for sure that this will affect precision. Do I want to really analyze this variable, right? Do I want to look for another variable that looks like it? Okay, I'm okay with having a negative impact on precision, but I don't want it to have an impact on validity. Remember that missing values will affect both validity and precision. How am I going to check to make sure that these missing values are not associated with loss of validity? We'll talk about that tomorrow. That's topic for tomorrow. That's a bit advanced, so discussions for tomorrow. But the point of today is just to say you have to inspect your data, right? And as you're inspecting, you're talking to yourself. It's not just it's not just happily scrolling down and say, oh, I see there are 7,000 missing values here. There's a lot of missing values for this variable. And so no. As you're looking at it, you are thinking and say, okay, this is a lot of missing values. I can't use these variables. But if I wanted to use a variable that has to do with cholesterol, can I use something else in my data set that gets at the same thing, even if it's different? So here I can say, oh, I can see this also has to do with cholesterol and has less missing values, right? Can I use this variable? Can I use it the way it is, or do I have to transform it, right? That's the reason why you're inspecting. It's not just scrolling down happily and just moving on, right? Those are the things that you must do first before you even start to analyze anything. And then you have to visualize the data set too, right? Visualization is such an important thing because it allows you to see they say a picture speaks 1,000 words. So yeah, so you definitely visualize your data set and see how it looks like. You can look at the mean value. Again, remember, everything we do in data analysis is two things. What is the answer and how sure are we? This is the answer, the bar, and this red bar, error bar, gives you how sure are we? So that's how I want you to look at all the things you do in analysis. What is the answer and how sure? We always calculate the point estimate and we calculate the measure of variance, a standard error, confidence interval, or whatever it is, to answer both things. What is the answer and how sure are we? So visualize a variable that gives you a sense of what is there. If it's of course the type of visualization for different variable types will be different. If it's a string variable like this, the visualization would obviously be a different type of visualization. Let's see what comes up. Oh, a word cloud, right? So that's why it takes a while. So here, for example, is a string variable. So the way we'll expect it to be visualized will be different than, for example, a variable that is categorical, like let's say this one. The visualization will obviously be different as well, right? So visualize your variable. It allows you to see distributions. So here, without any further analysis, I already know that, well, wow, it seems most of the people in this data set are called Davids, and then, followed by Sarahs, the first names. Wow, Sarah is a very popular name. I can see. So again, I've not done any single analysis, right? This is just by looking, inspecting my data set. And you can also change the type of visualization you have. I can say, okay, I want to change it from a bar to a pie. That's a very horrible choice. As data analyst, you must come to hate pie charts because they're not very useful for getting relativity. It's very hard. Think of this, right? The differences between the categories is not as obvious in a pie chart as you would have it, for example, in a bar chart, right? Here, just at a glance, I can see that, oh, this is the smallest guy here, Wilson. The fewest names belong to Wilson. So please, let's try to have a collective, these are very strong words, but a collective disdain. I say this in a joking one manner too, but a pie chart should not be your go-to chart as a data analyst, right? Especially when you're visualizing categorical variables, simply because it's quite hard to tell differences between categories in terms of their distributions. So you should prefer using others like, the column, where they are in a column, or bar, where they are inclined more horizontally, right? That way you get quick insights. So even before you've done any analysis, this allows you to be able to get like quick insights and see what the distribution of the data set is like. So that's also a very key part of what you do in inspection. So remember we said you take a history and then you inspect. Now let's go ahead and go back to our slides. So now we're done with inspecting. We've looked at all of these things. We open our data set, we checked, is there any data in it? Then let me add one more term here, just in terms of nomenclature and just proper grammar. Since we're all experts in this field, we must learn how to articulate words properly. So let me add data versus datum. Data is a plural of datum. Datum is a singular, data the plural. So we want to avoid terms like data was analyzed. It's like, oh, really? That's because remember data plural. No. So instead, we should have it as data were analyzed, because that's the plural form of it. The same thing with analysis versus analysis. This is the plural, the one with the E. The one with I is the singular. Why is this important? Well, because we're all going to become data analysts. And as professionals in this field, the way we communicate about data needs to be a bit more precise than people who are not in the field. All right, that's why we need to emphasize all of those terms, even if they seem like nitpicky. All right, so you take a history, you then inspect. At this point, we're not touching anything yet. You palpate, now you're touching, right, with your hands. We're not bringing any tools in palpation yet. So this is where we are now. We've taken the history, we've inspected. Now we have to palpate and touch things and move things around a little bit with our hands. No fancy tools yet. So let's see how that works out. So palpate, now we want to make some changes to data, rename variables. We want to recode variables. We want to replace values within variables. We want to generate new variables. We want to visualize. We want to specify. Those are some things that we just do to correct things. Maybe we want to clean up the data a little bit. Let's look at some best practices for variable names. Again, remember, things we do as data scientists must be fair aligned. Fair, once again, means that it has to be findable. It has to be, I think one of you should tell me what fair is. I'm looking at people. Are people able to talk?
They can type.
Okay, I'm sure they can type then. So fair, as my fellow data scientists and analysts, what does fair mean? What does a fair doctrine mean? Let me check. Everybody knows the F, findable. Okay. Excellent. All right, good. So so best practices for variable names. So when you're typing variable names, you have to keep in mind that it has to be interoperable. So know that different software have different rules for the kind of variable names they accept or they allow. So when you are giving variable names, please be mindful of that. If you're not mindful of that, what happens is that you give a variable name, you document it a particular way. Then when you share the data set, the person tries to import it, the platform there would coerce the data set and give it a new name that is different. Maybe you put a dot, the software removes the dot, throws it away, and puts underscore. That completely changes the name. The data dictionary now is no longer the single source of truth, right? Oh, let me add one more term, which we use a lot in data science. Where's my terminology sheet? So we'll talk about single source of truth quite a bit. It means, where do I have to go to find the absolute truth about anything? In the case of your analysis, this has to be your data dictionary, right? So you have to define a single source of truth for your analysis, like the code book. What is in the code book must be the truth, the whole truth and the only truth. It cannot change. But for that to occur, your practices must be fair aligned. You must make sure that you keep in mind that there are so many different software in the world that have different rules for how they manage things. At the end of the day, every software was created by a person or a group of people. And so you have individual preferences. Unfortunately, some of these things, there are no global standards, or the way software A handles it may be different from the way software B handles it, based on their different philosophies and maybe way of doing things. So you have to keep that in mind. And so to avoid any problems, if you follow these things, you're going to be fine every single time. Don't start the variable name with a number or a special character, no underscore, no. So start with a letter. The variable name should contain only numbers or letters. And if you really must use a special character, underscores is always safe, an underscore. Some software accept the dots, others do not. Some accept, certain characters, others do not. An underscore is one character that is accepted universally. Then don't make it too long, right? Because it has to be not just machine readable, but also human readable. If you give a variable name that is so long, then it becomes hard to understand it, and it should be intuitive. Now, this is not a technical issue. But your variable name should be intuitive. Like if I just read the variable name, I should know that, oh, this is talking about cholesterol. I don't know exactly what it's measuring, but I know it has to do with cholesterol. So if it don't, so the wrong variable name will be something like car, right? Or CX. This is wrong on so many levels. Who can share with us why this is wrong? Or let me remove this one first of all. Why would this be just a really terrible variable name to assign to your variable?
You may raise your hand if you want to answer verbally. Otherwise, you can also type.
Yeah, I think exactly. If it doesn't give any clue about what it's about, the variable name is not intuitive. This becomes so hard when other people are on the team and they take the data set and like, okay, CX, what could that be? Right? They have no clue. So please do not give a variable name like this. You can have something like you should develop your own philosophy for naming variables. For me, this is how I name variables. I may have a variable, for example, let's say I'm trying to name variable like current cigarette smoking in the past 30 days. So I will have current SMK. I don't use uppercase in my variable names at all. Everything is lowercase because, of course, most software are case sensitive. And some letters makes it very hard for you to know whether it's uppercase or lowercase. For example, letter K, it's hard to know that this is uppercase or lowercase. And and that could make a huge difference, in whether you're getting errors or whatever, right? So for my own personal preferences, I just use lowercase consistently. Now, that's not to say that you have to follow that principle. You all have to develop your own style, your own flair for doing things. But for me, everything is lowercase. The first name is always a descriptor of what that um, variable is measuring. And then I may have an indicator like O2 FS. So in this case, current cigarette smoking, it has two categories and it's in the full sample, right? Versus if I have, and this is just my own way of doing things, or I may have SS means subsample or subset. So just by looking at it, I can tell that, oh, this variable is measured in the whole population. And this has two categories, and this is current cigarette smoking, right? And then it's that pattern is repeated across the whole data set. So that when I share, once somebody understands the philosophy behind my nomenclature, then they can just look at it and say, oh, okay, that variable has four categories. It's very easy for them. Oh, how do you know it has four categories? Well, O4, right? If it's a continuous variable, I call it 00 to indicate that it's continuous. But that is just my style of naming variables. You don't have to follow that. You can create your own style. As an analyst, you're going to be handling data a lot of time. So you have to create your own style for doing things. But regardless of what the style is, you must make sure it's fair aligned, right? Data must be findable, accessible, interpretable, and reusable. Reusable by another person who comes along so that you don't have to start wondering, what's CX? It should be very clear what things are. And so now let's see how this works out. Let's go and see how we can rename variables, how we can recode. Recode means to change the code. Recode means that the code of a variable is changing. So we're going to see how those things can be implemented. So let's go back to our data set, which is this. Now we have taken the history, we have inspected. Now we want to palpate the data, right? Just do some touches, change some things. So let's say that we're interested in a variable like, let me look for a variable here. Okay, let's use that. Let's use this one. Glucose. This is was measured in the lab. I can see the serum. This is a very good name. Whoever renamed this is very considerate. It's a bit long, The variable names are a bit long for my liking, but they are at least intuitive. You can see that it's quite intuitive. You can see that this is glucose, although the person was trying to create a whole sentence from it, but that's fine. Any day, anytime, it's better to be clear and a bit more verbose than the other way around. So I rather have this kind of naming where it's a bit long, but I can understand what it says just by looking at it. So we know that this is refrigerated glucose was taken from a lab, it was captured from serum, and the unit of measurement is milligram per DL. So let's try and recode this variable. So when you come here, you can see this more options. That gives you, well, more options to do different procedures. When you click on that, you can visualize rename. You got rename means you're giving the new name. So if I want to shorten that name, I can just click there and let me enter the new name. So based on the standards we mentioned, I can call it glucose. If I don't want it to be too long, serum. Let's say milligram. I try not to have too many underscores. My own preference, again, you have to develop your own preference for these things, but try and keep it consistent. I just would like to have one single underscore in my data, in my variable names. So in this case, for my own usage, I was just calling it glucose milligram per DL, right? So in this case, somebody seeing this unit of measurement knows that this was still objectively measured. I'm not trying to tell them every single thing about the variable in the name, but it still keeps it usable, and I can keep it short and still informative. That's the point I'm trying to make. So that's how you recode variables, rename variables, right? You simply click there and rename, and you give a name that you want. So for example, gamma, right? And then you click on rename. And that's how renaming of variables occur on the platform. Now, if I wanted to, let's say, recode means we want to change the code, right? Each of these values, the unique values, is a code, right? So we want to recode. So let's say that I want to split the glucose variable, the blood level of glucose, into two values based on a particular cutoff. So I can come here and just select recode. So on the KiteForce platform, there are two ways to do any single thing. There's the easy way, and then there's the hard way. The hard way is for people who like to suffer. There are some people who like suffering. So we give them the hard way of doing things. But again, remember back to the very point we made earlier, your goal as a data analyst is not about the methodology. Your goal is to get accurate results. So don't worry so much about the tool. The tool is less interesting, right? Is it valid? And is it giving me the correct results? So to recode the variables here, I can click here to expand this. So let's say I want to cut this variable into two based on a particular cutoff level, let's say 120. From 120 and above, I want them to go in one category. And then below 120, I want them to come into another category. Why is that recode? Well, because we have the codes currently are 49 to 577. That's the current codes. I want to recode because I want to collapse those codes, change them. That's what we call a recode. So in this case, I want to split this variable at 120. So all I need to do is just click around 120. Well, I didn't click at the right place, so I can edit it to the exact thing I want, 120, and just click on confirm. And so the platform splits it. So you have 120 and above and 49 to this, right? So I've recoded that variable, but I can also still do another recode. This is the current code, 49 to this, but I may not want that code. I may want to change the code to, let's say I want it to be binary, right? As it is now, it is categorical. So I can just say, let's recode let's change the name of this category to, let's say 0. And let's change this one to 1 so that we create a binary variable. So now we have used the cutoff. So what we just did now is we took that variable that had all those values and we split it based on the cutoff of 120. Individuals who had 120 or higher, we put them in one category, which we called 1. Those who had below that cutoff, we put them into a separate category, which we called 0. And now you can see the missing values. The beauty of this visual method is that it is very intuitive. You can see it with your eyes. You can see what's happening. So again, this is a session for individuals who have no idea about data. So, but this is something that anyone can do. Just select the value you want and split on that value. And it's that simple. No, there's no coding, there's no trying to figure out what, geez, I'm getting this bug, this error. None of that, right? It's just click and put the value, cut, assign values, and that's it. You can also see, it allows you to also see with your eyes the missing values that you have at play, right? So here I can see that there are 3,622 missing values. If I want to first, let's say I want to say, oh, individuals who have missing values, we want to put them with 0. Well, I can just drag and drop that, right? And now it's now people who have 0 or missing, right? So the bottom line is there's nothing you can do with code that you can't do with visual methods like this. The goal is just to say, how do we empower people who do not know how to write code, but to do whatever it is that they want to do, right? The goal is about empowerment. But again, for people who want to write code, of course, you can choose whatever. The focus is not on the tool. Whatever tool you're using is irrelevant. The goal is to get insights from data, however you get it, right? And so here in this case, I have now recorded my variables such that individuals who were above 120 are in this group. Those who were below 120 or who had missing values are in this group. I can still choose to collapse this group into different based on the values there. But yeah, this is a visual way of analyzing data. Now, if you want to use the, let's go back to the recode. Let's go to, instead of using the visual method, let's use the classic method. The classic method allows you to do the same thing, but in a way that is less colorful. I've chosen the classic method. This is the variable. Now I want to add a new category. I have to click this, and I'll say if value of glucose this is greater or equal to, you put the value you want, 120, then change the range of values to 1. See, this is the exact same thing you're doing as before, but this is now a lot more complicated. Or I'll say a lot less intuitive. Now, of course, there's some people whose brain works a particular way and who will say, oh, this is how I want to do things. The point we're trying to say is that the tool itself is irrelevant. What the tool you're using, as far as it's obviously validated, it doesn't matter what you use. It doesn't matter whether you do this in Python, whether you do this in R, whether you somehow engineer your own process to do it, whether the goal is to generate accurate results and not to worry about the tool, right? So that's the emphasis we're trying to make, that it's all about getting the correct inferences and not obsessing about tools. Tools, tomorrow there'll be new tools, next tomorrow there'll be newer tools, but the results will always still be the same, all right? So here I say if value of this is greater or equal to 120, then change the range of values to 1. I can now say assign any remaining observations to a separate category and excluding missing values, right? And then I can now give it a new name. Now, I never ever use this classic method because I just find it very non-intuitive. I mean, I can write code all day, but if I can avoid writing code, obviously I will avoid writing code. So any day, every time, I always default to the visual method to do most of my work because it's just very intuitive. All I have to do is select the value 120. I confirm. It splits it. I just let me make this bigger. I just then change the labels to whatever I want. In this case, 0 and 1. And then I can now simply proceed, give it a new variable name. I can call this diabetes measured from the lab. Maybe I'm using that as a cutoff to say individuals with that blood level of glucose above this are classified as having diabetes, and those below that cutoff are classified as not having diabetes, right? So in this case, I've created this variable as a binary variable from that continuous variable. So if you now see, if you go to the top, you now see it's a binary variable, 0 and 1, right? These are the values here. If I visualize this now, you can see here we have, these are the number of individuals who reported 1. These are the number of individuals who reported 0. So this is what we mean by recode. You take the variable and you change its codes in a way that aligns with the research question, right? And that's one of the things we do with this. The same thing applies to categorical variables, right? Let's say I have a variable like race, and I want to recode this. Let's go to recode. In this case, let's say I have all these groups here, and I want to collapse them into 3 groups, right? I want to have white, black, and other. So white, I want it to remain as white. Black, I want it to remain as black. And then all these other ones, I want to collapse them into one group called other. Well, all I have to do is just drag and drop, right? And just drag and drop. And yeah, and that's how I record. Again, the goal is to make things easier for people, not harder for people. And then I can simply change the labels to whatever I want. Maybe I want to just call this black. And I want to call this white. And I want to call this other. All right. Now, so I have my white, black, and other. And now simply I can now give it the name, race. Of course, your data set cannot have duplicate names. That's very, very important. Any software you're using should obviously prevent you from having a variable name that is a duplicate. That's very well enforced on the chi-square platform. So I can only give another unique name. I always try for variables like this. My personal preference is to always give it as race 3. So in this case, that tells me that race has 3 categories. So that when I just look at the name, I know that okay, this is a number of categories I'm dealing with. You can come up with whatever philosophy you want to give your names. Those are not rules, obviously, set in stone. They're personal preferences. And then I can recode. So that's how you recode, right? So in other words, to change the category name such that you can collapse things together. You can also use the classic way if you wanted. Again, personally, I never use the classic method because it's just I love things that are intuitive. I love simplicity. I'm a huge fan of simplicity. So let's always make things simpler, not harder, right? Whenever we can. So here I'm going to create a new category and say a value of race is exactly what is containing any of non-Hispanic, Asian, multiracial, or Hispanic, right? Then change the range of values to, let's say, other, right? So we want to create the other and race 4. So that's how you create that, let's go back to the slides, what that does that in the background. So here, for palpate, you rename, we recode, we replace values, generate new variables, visualize variables, and respecify variables. Now let's touch briefly on this one here to create new variables. let's say that we want to create a variable such that we have a variable created from an individual that says whether you have self-reported diabetes or you have lab detected diabetes. So here we have, let's say, two variables for diabetes. One is self-reported, which is yes or no. The other one is from the lab. So we want to say if you answered this or this, then we classify you as having diabetes, right? To do that, we just come to, again, data processing and create composite variable. A composite is something that is made up of two or more things. So here we're trying to create a new variable from two or more variables. So we're going to click on this and say using conditions. In other words, conditions means rules, right? So conditional statements are those that says if. That's the most important word, by the way, one of the most important terms in data analysis. If. So once you see the word if, you're referring to conditions. So want to create a new variable using conditions. And the variable we want to create is based on diabetes from a lab, as well as self-reported diabetes. So we'll select those two variables. So let me make this bigger. So here we're saying if you answered, your values of diabetes are this or this. So if you say yes or one, then that means that you have a classification of being a diabetic. So we're going to drag to that side, and then we'll assign all remaining observations into the remaining category and exclude missing values. So now here we have individuals who answered yes or no. This is our group here. So we're going to label them as 1. And then the other ones, we're going to edit them as 0, right? And that's how we create that group, right? Let me take that again for people who didn't, if that was too fast for certain people. So let's just reset this. And by the way, there are sound effects, which if you don't like, you can always put them up from here. So let's start all over again. We said you are said to have diabetes if you have, from a lab, you have 1, or from self-report, you have yes. So we apparently want to combine this group and this group. So the visual method is simply saying, just drag things to where you want them to go. That's it. So I can simply drag this guy here. And when you drag it, the platform is going to ask you, what's the relationship between the two? Is it or, is it and? So obviously in this case, it's if you answered yes to this, or you answered 1 to the other, right? So the relationship between them is or. So you select or. And that creates a new group, which is yes, you answered yes, or you said 1. So that means we've created this group. So we can now drag it to this side, which is for where we have the merged variables. Every other thing that is remaining is for individuals who do not have diabetes, minus the missing values. So that's what we're saying. Once you create one category, the platform gives you the opportunity to, instead of having to spend time and effort trying to recode the other ones, well, you just have this shortcut. Just say, oh, assign all the remaining ones into the remaining category, and you can now choose to include missing values or exclude missing values. That's up to you. Ideally, we always exclude missing values to prevent misclassification. So if you exclude missing values, it then takes the remaining observations, creates the new group, and you have the missing values preserved. So now I can then edit the label. This is 1, and this is 0. So that's how that works. So just repeating for people who did not see that clearly. So now there are lots of validations in place to make sure that you didn't make an error. So for example, that you don't have overlapping groups where an individual is in both categories. So that is what is done automatically in the background with conflict resolution. So just click on conflict resolution and give a name. So here, this is called any diabetes. So let's proceed to conflict resolution. The platform will detect if there are overlaps. If there are, it will address them. If they're not, it will. So now we have any diabetes created, which is also a binary variable 0 or 1, right? And so that's how the platform allows you to be able to create variables in a very intuitive manner. So going back to our documents. So rename variables, recode, replace, and replace is always very important because you might want to replace certain things. Let me quickly show you how to do that. So if you want to, let's say, replace a particular thing, and this is very intuitive, really. You can simply come from here, data processing, or you can come from the side and come to replace. It's asking you, do you want to replace specific variables or the whole data set? In this case, we've already selected diabetes. That's the variable we want to replace. You find the value you want to replace. And if it's missing values, you can also select, okay, I want to find missing values and I want to replace them with, for example, 1, right? Or if I'm finding a value like 9 or 0, again, you can do that exactly. Or if you want to replace the value with missing values, you can enter the value. I want to find all values of 1, and I want to replace them with missing values, right? So in that case, the system goes systematically and replaces all of them accordingly. All right. So that's, I think we've covered that for all of the items there on the palpate. And then let's go to the last item, inspect. We say we inspect, we take a history, we inspect, we palpate, and then we auscultate, right? When auscultation is simply bringing, now when we are using a tool, right? Also far, we're just using our hands or ears. Now we're bringing a special tool, right? So that's exactly what we're doing when we're also trying to, look at data at the beginning. We want to auscultate. In other words, we want to test things. Are there differences? When you're doing analysis, right, all the things we've been doing so far involve one variable, right? We're just been like, we visualized one variable, we recorded one variable. Well, we created a composite variable from 2 variables, but it still involves one new variable created at the end. But your analysis should not just end up just looking at one single variables, right? Your analysis should look at a framework of, let's go back to our sheet and let's call this framework. You should have a 1, 2, 3 framework, right? 1 variable, 2 variables, 3 or more variables. We call this univariate, right? That's all we've been doing so far. We visualize a variable, we do this, it's univariate analysis. That's what we've been doing. And here, again, let's go back here. When we come to diabetes, I would say, oh, let's look at the summary of this diabetes variable. I would check and say, okay, 87.3% reported 0 and 12.7 reported 1. That's univariate. Why is it called univariate? Because we're looking at one single variable. Uni means 1. Think of the word unity. We are all 1, right? So univariate means looking at one variable only. Or if it's a continuous variable, let's clear this away. I will look at the summary. I will see all of this. Those are all univariate. So here, for example, we see that the minimum value is 4, the Q1 is 13. Those are all univariate, right? Let me make sure we all understand what these terms mean here before we leave this univariate and go to bivariate. The mean is the average, right? They will take all of the values and take the average. That's what the mean is. I think from a lay perspective, that's the most common of all of those metrics. People always say, well, on average, how much is it? So on average means we take all of those different values and we take their common average and say, okay, this is the number that represents all of them. The standard deviation tells us, in general, remember we said for everything, we're interested in the answer and how sure are we, right? It gives us a measure of variance of how observations fall far from that, that mean. The minimum is the smallest value. The maximum is the largest value. These 5 numbers, 5 values, minimum, 1, 2, 3, 4, 5, together make up what we call the 5-number summary. And that's something that you have to know. Let's add that to our terms. 5-number summary. You must know that term because somebody would say, oh, please, can you give me the 5-number summary? You shouldn't be asking them, huh? What did you mean? 5-number summary. So the 5-number summary are those 5 numbers that tells us about the distribution of a particular variable, continuous variable, or numeric variable. And so the 5-number summary comprises the minimum, the first quartile, the median, which is the second quartile, the third quartile, and the maximum. Those 5 are what we call the 5-number summary. The difference between the minimum and the maximum is what we call the range. So when you say, oh, what's the range of a data? It ranges from 4 to 1510. So that tells me that 100% of the data falls between 4, which is a minimum, and 1510, which is a maximum. That's what we mean by the range. Now, between the Q1 and the Q3 is what we call the interquartile range, right? The interquartile range. This tells me that 50% of the data falls between 13.0 and 26.0, right? So that's what those numbers mean. You have IQR or interquartile range. You need to understand what they mean and what the interpretation. So this means that it's called a 5-number summary because, let me take a screenshot and let's look at it quickly. My print tool. So that would make it a bit more visual so you can see what I mean. So let me take a small snippet here. So if you think of a box plot, Lumile, can you confirm when I see this box plot I'm drawing?
Yes, we can.
Okay, all right. So it's called a 5-number summary because it tells you the distributions, the 5 main points of the distribution of the data. So each line is a part of that 5-number summary. This is 1, 2, 3, 4, and 5. There are 5 lines. There are 5 vertical lines. That's why we have a 5-number summary. This is called the minimum. This is called the maximum. This is called Q1. This is Q2, which is a median. This line in the middle, obviously, is a median. And this is Q3, right? So between any of these two, any two of them is 25%. From here to here is 25. Here to here, 25. Here to here, 25. Here to here, 25. Between any 2 vertical lines is 25% of the data, right? So that means that between here and here is what percentage? Any answer for us? Exactly, 50%. What of between here? Oops, I'm running out of space. What of between here and here? What percentage is that? Still 50. What of between here and here? Still 50. So the interquartile range is saying, oh, I just want the 50% in the middle, right? This is what the interquartile range is saying. The 50% that is in the middle is that's why when you hear IQR, they're just saying, oh, what percentage is in the middle that makes up 50% of the data? You need to be able to get these numbers and interpret them. So when somebody says, what's the IQR from the data, they're saying, oh, the middle 50%, where does it lie? So you're going to say, oh, the middle 50% lies between 13 and 26%, right? That's where the middle 50% lies. The median is 17. And so these 5 numbers together make up the 5-number summary. So again, as data analysts or data scientists, we all have to know the 5-number summary. So when somebody asks you for it, you can provide them, right? And then they going back to our framework, we're talking about the 1, 2, 3 framework. All right. So when you're doing your analysis, this is the mind frame you want to have. You want your analysis to follow a 1, 2, 3 format. 1, 2, 3. 1, 2. It's always 1, 2, 3, right? 1, univariate, 2, bivariate, and 3, multivariate or multivariable. So 1 variable, 2 variables, and 3 or more variables. That's the flow you want to go. So if I have an intern and I give them some data set and they just start telling me, oh, the results from I did regression, I'm like, calm down, right? Before we go to regression, can you give me an overview of what the data set is all about, right? So I expect you to tell me that, oh, I did the universal analysis, the mean value was this, right? 1, 2, 3. Remember, always 1, 2, 3. The mean. So let's say I told I give the internet data sets. Remember, we said you got to have a conversation with the boss and say, oh, what do you take a history of a data set, right? Where is it coming from? Okay, what are we interested in? What are you interested in? I'm like, oh well, I want to see the mean intelligence quotient, right, or the IQ levels, and I want to see how it differ by, let's say, gender. So the intern comes back. What I expect is that you're going to start with univariate. You're going to tell me that, well, in the overall population, the mean levels of this variable was this. I'm like, oh, interesting. And then you can go ahead and describe, oh, okay, the median value was this, the interquartile range was this, and I'm like, okay, great. And then I expect this person to then go ahead and tell me about the bivariate, right? You should be able to tell also, if you look at this here, as data scientists or data analysts, you must be able to tell just by looking at the data where data is. So let's go back to this summary. All right. So my question to you, is this data right skewed or left skewed or normally distributed? What do you think? Right skewed, left skewed, or normally distributed? These are some things that you should be able to just tell automatically just by looking at something like this. Okay, I need somebody to raise their hand and defend their answer. Okay, do we have a volunteer?
Peter.
Yeah. Based on the distribution, we can see that it is right skewed because most of the data or the variables we examine first at the right side, because looking at the minimum value, which is 4, and I'm coming. And the upper quartile having about 1.5. I cannot see my full screen.
Okay. All right. Thanks for that. Thanks for that attempt. Any other thoughts? Any other volunteer?
Kesid.
All right, good day. So I think it's left skewed because even the median, which is supposed to be the half line of the 50%, it's towards the left. It's 17.0. So even the Q3 is also on 26, which is not even at the 50th percentile or half of the data. I think it's left skewed.
All right. Let's understand. Let's establish some things in as first principles, right? And then I'm going to ask another volunteer to now explain to us after we've established this. So how do I clean this? Okay. Oh man, I should have just grabbed the new screens. And anyway, this will work. All right. If it's normally distributed, in the middle, we're going to have the mean and median are going to be equal. So The trick to answering that previous question was two things only that you need to look at. You need to look at the mean, and you need to look at the median. That's the only thing you need, nothing else. Look at the mean, look at the median. When it is normally distributed, the value of the mean will be the same as the median, right? And also remember that the median always stays in the center. That's why it's called median. It will always remain around the center. So in the three diagrams I'm going to draw, the median will always remain on the center. Now, let's say this is another distribution here. Oh, I can actually draw beyond that. Oh, nice. All right, let's say this is another distribution here. So the median is more or less always staying in the middle, right? The mean, however, always go towards the tail, right? Always think of mean tail. A dog, you can know where a dog is mean if you step on its tail. So that's very bizarre mnemonic, but just remember mean tail. The tail is associated with the mean dog. So the mean always goes to where the tail is. So, but remember the median is always in the center. So here, the tail is this way. This is the mean over there. And remember, in English, we read from left to right, right? Unlike Arabic or other languages. So the numbers are increasing as we go here. So in this distribution, this is right here, it's right, and right skewed. Which one is bigger and which one is smaller? So remember, the median is always going to stay at the center because median, middle, the mean tail means the mean goes to the tail. So here in the right tail distribution, which number is bigger, the mean or the median? Yeah, the mean is bigger than the median, remember? So that means that if you look at two numbers, again, your job is just to look at two numbers and say, oh, this is right tail, this is right skewed. And then everybody's like, wow, how did you know that you're so smart? Right? No, it's not a magic trick, it's simple. Look at the two numbers, the mean and the median, and see which one is bigger. If it's the mean is bigger than the median, remember, the median is always going to stay somewhere in the middle. And in this case, the tail drags the mean. Remember, we read from left to right. If it's left skewed, that means that the mean is going to be smaller than median, right? Is that clear to all of us? If you're confused, give me a thumbs down. Is there a thumbs down app? I don't know why don't these platforms ever provide thumbs down? This is just a way of endorsing. We need endorsements. So like thumbs downs are removed. They're not allowed. All right. Okay, if you are confused, just raise your hand. Okay. Can somebody who understands explain? Oh, Lungi, thanks. I see it. There's a thumbs down. Okay, sorry about that. I didn't know that. Okay, let's go back to our so here. Now I want somebody to explain to us then, so that all of us can get it, about why we conclude that whether this is normal, left skewed, or right skewed.
Diana?
Hello. So following the explanation, we know for this data set, our median is 17 and our mean is 26.08. So since our mean is bigger than the median, our data is right skewed. Over to you.
Very good. All right, good. So you answered excellently. Now let's go back to our framework. Remember, we said for any analysis, you take a data set. When you take a data set, as a good analyst, you want to take the history, then you want to inspect, you want to palpate, and then you want to auscultate, right? Just like every doctor does. I would say that when you're analyzing, you want to do a 1, 2, 3 approach. 1 is univariate, 2 is bivariate, 3 is multivariable. And that's what we're going to follow through for the next few days. Univariate, bivariate. Bivariate is asking the question of, is it different? So if I'm asking, for example, if I'm interested in mean height, people's height, univariate will tell me that, well, the mean height was this, the median was this, the interquartile range was this, the range was this. It's all focusing on one variable. But bivariate has to do more than that. It has to look at two variables. And so in this case, I expect my intern to tell me that, well, the mean height was this among boys and so among girls, right? It's not enough to just tell me that boys were 5 feet and girls were 5.2, whatever. I want to know, is that difference significant? Is that a significant difference, right? And so that's why we have bivariate analysis here. One of the things that's very hard for people who are new to data analysis is to keep memorizing all the statistical tests that one has to do for any particular analysis, right? On the Kairos platform, you don't have to worry about memorizing things. Let's say I want to measure the levels of blood glucose, and I want to compare between males and females. What kind of statistical tests should I use? Let's say this is the test here. This is the glucose we want to measure, and I want to compare the values between males and females. What test would that be? Okay. Okay. So now, if you don't know, if you know that's two sample tests, great. Now, if you don't know what test to use, you can simply come here to Analysis Wizard. The Analysis Wizard is designed for people who don't know what they're doing or who are not sure of what they're doing. It's designed to help you. So you don't have to start memorizing all the tests in this world. Like, why? You should save your brain for something else, not just memorizing things. So here you just come and select the statistical test checker, and you select the variables you're interested in. In this case, glucose, and the variable for sex, which is male and female, and that's a categorical variable. And all you need to do is click on Run. So the platform takes that information, it will determine the kind of test itself, and it will run the test itself, interpret the results for you, and give you the answers so that you can then use it for whatever you want to do, right? So that your focus is not on, your focus is not on, oh, geez, what kind of test? You know, some people actually carry around charts where they say, oh, if it's categorical and categorical, use this test. If it's this and this, use this test. Well, you can, if you like to suffer, you can do that, and that's fine. But again, with technology, we don't have to memorize those things all the time. Now, nobody mentioned that it could be a Welch test. Now, in this case, it just so happened to be a two-sample t-test. A two-sample t-test assumes that they look at the groups here, that variances are equal between the two groups, that the variance in the outcome is the same among males as among females, right? But most people ignore those parts, right? They just oh, when it's two groups and you have a continuous variable, then you use a two-sample test. Well, that's technically not very accurate, right? So the advantage of a platform is that it will know whether to implement the standard t-test. So what we have here is a standard two-sample t-test versus a Welch test in the cases where it is not normal. So you don't have to tell it. You don't have to, do any of that, right? The platform will automatically test the variances and will then implement the right test, right? So in this case, all you have to say is to interpret the results and say, and it also interprets it for you. It says, in this case here, the two-sample t-test was used to test the null hypothesis that there is no significant difference between the means of two independent samples against the alternative hypothesis that there is a significant difference, assuming equal variances. That's a very important statement. And how did the platform know this? It actually tested the variances. It tested the variance in the mean values of the outcome between males and females. First, it discovered that there was no significant difference in the variances. And then it now said, okay, based on the fact that there's no difference in variances, here is an appropriate test. If there had been a difference, it will have automatically then said, well, we're going to use a Welch test instead. So it does all of that algorithms for you so that you, as somebody who is new in data science or data analysis, don't have to worry about it. Now, If you want to test yourself, is there any harm in that? No, absolutely not. You should do that. But for those who don't even know that they're supposed to do that, the platform serves as a safeguard for you so that you don't end up doing the wrong things. So in this case, the mean values of this outcome was significantly higher among this group, male versus female, and these are the mean values with a p-value of this. We'll talk about interpretation of p-values down the stream, but for now, we're just focused on the very, very big picture. All right, so that's the end of our class. We're going to stop there today, but the bottom line is today's session was just easy peasy. How do we read data? How do we export the data? How do we inspect? How do we do all of those things that we need to do? I will take questions if there are any now.
Thank you very much, Prof. Thank you very much. I saw a few questions posted earlier. Could you kindly repost the questions and then I will read them out? Should you have, okay, I see people have raised their hands. We're also going to post the attendance link right now. So look out for it and please complete it if you would like to receive a certificate. Okay, so I'll start by Micah. Start with Micah.
Oh my God, thank you so much. I think my hand was, I wanted to make a comment about the distribution for the data that was presented by Professor, but then I would like just to thank Professor for having done such kind of a brilliant presentation. Thank you.
You're welcome. Thank you.
Okay, thank you. Chinonso. Emmanuel. All right. Bismarck.
Thank you very much, Prof. Prof, I am curious to know, maybe we'll get there from tomorrow, but I'm curious to know because I'm so much impressed of what I'm seeing here. It makes statistics very simple. But the question is, I'm asking an advanced question, forgive me. Can we use this chi-squares to analyze data that has to do with quasi-experimental, like propensity matching, and then you talk about the difference in difference and all that. Because I am working on my data for my master's, my second master's, and I wish I wanted to use state, but from what I'm seeing, I think it will be so easy for me to use chi-square. So is it possible that I can use the platform to analyze PSM and then DID?
Yeah, so all the tools are there for you to be able to do that. There are vast amounts of regression methods in the platform. But also one of the things we're also doing is to really not make things harder for people, but make it more simple. So we want to, like, one of the things we're going to implement in the next release for people who may not be able to take those regression methods and construct what they need is to explicitly say, these are the buttons you need to click to get this methodology, for example, difference in differences, right? So it's explicitly there. Or let's say, you know, I want to do an interrupted time series too, for example, or whatever it is you're doing. So but bottom line, yes, the tools are there for all sorts of, for various types of regression, but we are working on the next release, which will explicitly provide all of those things as distinct methodologies of their own.
Thank you very much.
You're welcome.
Ibrahim.
All right. Thank you, sir, for this wonderful presentation. Very insightful and informative. Thank you very much, sir. Yes, sir. While you are explaining the history, you made mention that the data analyst will like request for documentation. I believe the documentation you are referring to are the tools or the questionnaires maybe that were used to collect those data. So what of in the case of where you want to blind the data analyst and you don't want to like present those tools that you use, you just wanted to like give him the raw data in order to minimize bias. What of in that case? Will you still like present the documentation as requested by him. Thank you, sir.
All right, thanks. So here's what we're saying, right? Look, please confirm that my screen is still on. I can't. Can you see my screen?
Yes, and Heinz?
Okay, all right, okay, great. So any data set, your short answer to your question is yes. Even if there was blinding, what is this variable called SMQ? Is it smoking? Is it? I still need to know what the variables are. Now the variable that assign people into, let's say, treated or control group is just one variable that may be called intervention. I don't need to know what group 1 or group 2 means, right? Because I'm being blinded. But I need to know that that variable is called it. You can't call the variable ABC, that's the variable name, and say, oh, because it's blinding, how am I supposed to analyze the variable if I don't know that that variable called ABC is the variable for the intervention, right? It becomes impossible to analyze the data. So yes, in any circumstance, you need documentation. Now, the documentation doesn't have to tell you that group 0 is the intervention arm or group 1 is the treatment arm. That is the information you don't need to know, but you still need every other information. So every single data set, take a good lesson from, for example, public data sets like in Haynes. Every data set you have has extensive notes for the documentation, right? You have a release note, you have laboratory data, you have, there is extensive information on every single thing because you need it. If you don't have it, how are you going to analyze the data, right? It's almost impossible. And so when you download a data set, again, you have what each thing means. For example, if I'm interested in, chlamydia, for example, you see the documentation file and data file. Those two things must be together. Like now I can open this and I can say, okay, wow, this is the title, this is the data file, this is a SAS transport file, the date of publication. This is how I expect all of you to write the documentation if you're the one generating the data set, right? And you should also have your name. This was prepared by so-and-so. And so you have all of this information, including the variables that says, okay, this variable, this is the name of a variable, this is the label, this is what the values mean. So here a value of 0 means it's indeterminate, a value of 56 means it is, the value of dot means it's missing, the value of 3 means indeterminate. How am I supposed to know a value of 3 is indeterminate if it is not documented, right? It is impossible. I just have 1, 2, 3 and missing, and I'm like, oh, this is an integer, or this is a numeric variable. Oh, you analyze data completely wrong, because what you did not know was that this is not a continuous variable or a count variable. This is a categorical variable. It just happens to be labeled as 1 and 2, where 1 is positive, 2 is negative, 3 is indeterminate, right? So the moral of the story is that you always need a data dictionary or documentation. And when you also give a data set to somebody as an analyst, it is your job to make sure that you're giving them a data set the same way we have it here, right? You give them the data set on one hand, data file, but you also must make sure you provide them with documentation on the other hand. The data set and the documentation must go together. All right, any other questions?
Thank you, Prof. No hands, okay.
All right.
How do we receive assignments?
Well, the assignment is in the let me go back to the document. Sorry, hold on, the spreadsheet. So it's a very hands-on practice. From the data set provided, let's explore the following. What percentage of a sample are male versus female? So you go to the data set. The variable is sex. So this is the variable here. What percentage of this are male and what percentage are female? That's question 1. What is the average value of a variable total cholesterol in milligrams per DL? So you're going to look for that variable. This is it here, column L, right? It says what is the mean value? And then the next question is, how do the average values of this compare between male and female? You're going to calculate the average values. So I didn't show you that part, but you come to estimate mean. select your outcome. In this case here, whatever the outcome is, and select your variable for gender, in this case, sex, right? And then you're going to calculate and then you're going to run the estimate in the overall population, and then says, how do the average values compare between male and female? That's how you're going to get values for males and values for females. In your opinion, is this difference big or small? This is just asking your opinion. Then from a statistical perspective, is the difference significant or not significant? And then it says you should inspect the data set and see the variable age. And it's asking you that by inspecting this variable, what problems do you see immediately when you look at it? You need to be able to develop the art of spotting problems immediately. So that you just look at the variable and say, oh, that's a significant problem there. So this is testing your ability to do the spot diagnosis of problems. So we planted, this is a mock data set. So we planted a lot of problems and issues for you in the data set, so you can discover them yourself. So yeah, so you can try, so that's the homework. And so you can try that and to practice what we've covered today. All right, any other question?
Yes, Prof. What is the difference between multivariate and multivariable?
Oh, we'll cover that on day number 3.
Right. Ray.
Good evening, sir. Good evening, Professor. My question is, how are we going to submit the assignment?
You can submit it on the on our what do you call it now? Lungile, you want to answer that question, please?
You can send it to education@chi-squares.com.
So that's the email.
I think Prof wanted.
Or you can
Yeah,
also
that's an email.
Yeah, or you can also post
LinkedIn.
it on our LinkedIn. Thank you. That was the term I was trying to look for. You can also post it on our LinkedIn channel. I completely blanked out on that name. All right, I think we're all done, right? All right, thanks everyone. See you tomorrow there.
Thank you very much, Prof.
All right, bye.
No, not a DM message. So we posted the assignment, right? Sorry, the flyer. So you can comment, copy. I'm just gonna send this. I'm gonna post this here. So basically you can post it as a comment in response to the flyer. It's easier that way. For the slides, just check our LinkedIn page tomorrow morning. We would have posted them by then. Yes, the assignment is on the chi-squares platform. So this flyer, the flyer here, I just posted the link. There's a flyer there. And you'll find the assignment in one of the pages. I think on day 1 page. So you can download the flyer if you don't have it yet. And you will see on page 3, page 3. Yeah. So session 1, page 3. That's the attendance link. Okay, the assignment we've been sharing. So all the reminders, they have all the, if you check the links, you will find everything there. But we'll share the flyer again, but it is on the WhatsApp group. It's on the Telegram group. Live stream, okay.